Very good afternoon, all the esteemed participants. I'm Professor Pravat Kumar Rai. Sir has already joined. We are going to start the session very soon. Before starting the session, I want to introduce Sir. Uh, Professor Pravat Kumar Rai received the BE degree in electrical engineering from Indira Gandhi Institute of Technology, Sarang, Odisha in 2000. The ME degree in electrical engineering from Indian Institute of Engineering, Science and Technology, Shibpur, Howrah in 2003, and the PhD degree in electrical engineering from National Institute of Technology, NIT Rourkela in 2011. He he had worked as a postdoctoral fellow from January 2016 to June 2017 at Nanyang Technological University, NTU, Singapore. He is currently serving as Professor Electrical Engineering in NIT Rourkela. He has around 20 years of experience in teaching and research. He has supervised 10 PhD students. He has published his research outcome in more than 70 research papers in reputed journal including IEEE Transactions, IEP, Elsevier, etc. He has edited 2 books and contributed 13 by funding agencies such as GST, GST Imprint 2, ACRB, Indo-Asians, and Indo, Thailand, etc. He has visited 6 foreign universities, which includes Queen's Mary University of London, UK, University of Southampton, Malaysia, University of Mataram, Indonesia, Waliak University, Thailand, etc. as a part of bilateral collaborative research. He has delivered 27 invited talks, including at foreign and Indian universities. He has organized 9 short-term courses and faculty development programs. He has organized 8 conferences, special sessions, panel discussions, etc. He is working as associate editor, IEEE CSEE Journal of Power and Energy Systems, and as guest editor of special issue entitled Advances in Control of Photovoltaic and Microgrid System, Journal Energies Publishers MDPI. His research interest includes estimations and filtering in power systems, power quality, power management in hybrid AC/DC microgrids, smart grids, solar irradiance forecasting, and renewable integrations. And very warm welcome, Professor Pravat Kumar Rai, in our session. Okay, so good afternoon, sir. Please, if
Thank you, Professor Arnav. Good afternoon to all.
Thank you, sir.
I'm sharing my slide.
Yes, sir.
Now my slide is visible.
Yes, sir. Your computer screen is visible.
Slide is visible.
Now slide is visible, sir.
Should I start now?
Yes, sir. You please start.
Okay. So today we'll discuss regarding forecasting of solar irradiance. So here this total talk divided into 2 parts. In the first part, I will discuss regarding solar irradiance forecasting using model based. And second part, I will discuss solar irradiance forecasting that is on image based. So in the first part, solar irradiance forecasting that is model based, I will discuss different types of machine learning or say artificial intelligence techniques, that is based on recursively square Kalman filter, then Ensemble Kalman filter. So main proposed algorithm here is the Ensemble Kalman filter. And in the image based, I will discuss regarding variable Leaky least mean square based algorithm, how it is used for forecasting of solar irradiance. Now coming to introduction regarding the forecasting of solar irradiance. So all of us know that because of increasing rate of climatic change and global warming, people are more concerned about the impacts of generating electricity. If we'll go for the fossil based fuel based generating electricity, then what are its impacts on this climatic change and global warming? That's why now people switch over to renewable based sources such as solar, wind, hydroelectric, biomass. uh, Out of this, PV act as a potential candidate or suitable candidate for this as a main renewable energy sources. But the main disadvantage or lacuna in PV is that uncertainty of solar PV generation, because we don't know after 1 hour, after 2 hour, how much will be our solar irradiance, accordingly, how much will be our generation. That's why it is highly uncertain. So uncertainty of solar PV generation results in the need of larger energy storage. That's why we have to go for the energy storage. We have to store our energy and we have to use as per our need. So when storage comes into picture, then more cost involved. So at that time, what you have to do, that we'll discuss. So how the irradiance changes. So change in solar irradiance, it happens when large cloud covers the sunlight. So when large cloud cover the sunlight, then power output of solar PV decreases. Irradiance become less, so we'll get less power from PV. So when we'll get less power from PV, then what will happen? It affects our system frequency and voltage also, because power we are getting less. So at that time, if we'll go for the energy storage at the only solution, then it more cost involved. So we require some ancillary services to meet these challenges or change in electricity supply. So that requirement is the need for precise solar irradiance forecasting. Means if you're able to find out or if you're able to forecast or predict how much will be the irradiance after 2 hour, after 3 hour, or after 1 day, after 2 days, like this, that is called forecast horizon. After how much time you want your forecast or your prediction, that is called forecast horizon. So if we'll able to forecast or predict what will be the solar power, PV power after this much or on this day, then what we will do? Then the operator can take the preventive action. What are the action? For example, so many sources are there in a system or a grid or say microgrid. So many energy sources are there. So when we require say this much amount of load, but at that time we have predicted that solar is incapable, then we have to go for, or we have to switch off the solar source. We have to go for other type of sources. Accordingly, the schedule we can arrange so that operators will be able to make in time preventive measure which source is to make on, that operator can schedule. So in the scheduling, dispatching and regulation can be easily possible if you'll able to forecast the solar irradiance. That's why there is requirement of forecasting of solar irradiance. So now how will forecast the solar irradiance? This is just a model. So in this model, first collection of monthly average daily global solar insolation data. So these data from the different meteorological site, we can get what is the daily global solar insolation data for a particular place. For a particular place, how much is the global solar insolation data? So if you find out for every day how much, so from that we can find out in the monthly average, in a month, what is the average of daily daily global solar insolation data. So taking that data, That is one part. Another part is extraterrestrial horizontal insolation. What do you mean by extraterrestrial horizontal insolation? Extraterrestrial horizontal insolation means the whatever irradiance or insolation available on the Earth's surface without atmospheric effect. So without atmospheric effect, how much is the irradiance available on the Earth's surface? That is called extraterrestrial insolation. So that we can find out from a model or from some equations are there. So what are the inputs required? Inputs required are, for example, in a particular location, you want to find out the extraterrestrial horizontal insolation or say H0, then the data minimum data required is latitude of that location and on which day you are finding out, day of the year. So day of the year means, for example, January 1st, you can take as 1, December 31st of a year, you can take as 365. That is the day number. So giving input latitude of the location and day number, we can find out the H0. So after finding out H0 and previously found out a monthly average global solar insolation. So that monthly average global solar insolation divided by H0, that will give us the KT. What is KT? What are its role? That also discussed. So after finding out KT, what is KT? KT is the clearness index. Clearness index means atmospheric effect we have to take into account when we will consider KT. That is clearness index. So after getting this KT value, we have to model KT. Then in that modeling, we have to use modeling using different, say, signal processing technique or say artificial intelligence technique, such as, because Professor Ganapati Panda already taken the first class, is discussed different techniques such as recursive least square, Kalman filter. So the different types of using different types of technique, Ensemble Kalman filter, recursive least square, Kalman filter, we have updated that KT value. And final update, final estimate of KT we have to find out. So after getting the final estimation of KT, and this H0 initially we have calculated for a particular location for a particular day, that KT into H0 will give us the forecasting of global solar insolation. In detail, we'll discuss all these steps. So whatever we have discussed, that is monthly average of daily global solar insolation. Generally, we can find out from the meteorological site data. Data should be collected such that it covers a large area of latitude. For example, if you want to find out for throughout India, then you have to cover a large area of latitude data from southern side, northern side, eastern, western, and central side. So from different side, you have to take the data so that it will cover a large area of latitude. These data are then reduced to monthly average daily clearness index KT. How to find out KT? That we have already discussed. So KT equal to whatever monthly average daily global solar insolation data we have collected divided by H0 of the particular place for a particular day. That will give us KT. Then H0, how to find out H0? We have already discussed that H0 you have to find out giving input latitude and this day of the year. And what are the other parameters required? How to find out H0? That we'll discuss. This extraterrestrial horizontal insolation, that is H0, for a day at a given place is the insolation on a horizontal surface at a place without atmospheric effect. So this H0 equals to 24I0 by pi, this expression, which involves phi, delta, omega SI. What are phi, delta, and omega SI? And here I0 one term is there. This I0 is nothing but this is the expression where I0 is the extraterrestrial irradiance in kilowatt per meter square. And here the I0 requires ISC. ISC is nothing but solar constant, which is 1.367 kilowatt per meter square. So that is the rate at which energy reaches Earth's surface. That is a constant value you have to take. And the another unknown is N. N is the day of the year, just like I have discussed. January 1st, you can take as N equal to 1, December 31st as N equal to 365, and in between, you can take the N value accordingly. phi is the latitude of the location in degree. So with this parameter, we can find out I0, and other unknowns are delta and omega SR. What is delta? Delta is the declination angle in degree. It can be found out from this expression. What is declination angle? Now, declination angle usually varies due to tilt of Earth on its axis of rotation and rotation of Earth around the Sun. Because of that, delta will vary, and we'll find out delta using this relation. And omega SR is the solar angle or the hour angle at sunrise. So omega SR, how to find out? This is basically time in terms of angle. Omega SR is nothing but the time in terms of angle. For example, solar noon is taken as at 0, and before noon minus, and after noon plus, and each 15 degree per hour time we have taken per hour 15 degree. For example, morning 10:30 a.m. Morning 10:30 a.m. is 1.5 hour before noon. Since 1 hour corresponds to 15 degree, 1.5 hour 22.5 degree, and since it is before noon, so minus. So that means 10:30 a.m. can be expressed as minus 22.5 degree omega SR. And omega SR can also be found out from this latitude and declination angle in this way. So knowing all the values for a particular location and for a particular day and for a particular time means we have to input omega SR. So giving all these, or after knowing all this data, we can find out this H0, that is extraterrestrial horizontal insolation. So H0 is one part, that is over. Next part is regarding KT. So here, while calculating H0, we have not taken into account the atmospheric effect, but actually in real, we have to take into account atmospheric effect. So that's why atmospheric effect at a particular place on the insolation is determined by this clearness index KT. It is a stochastic parameter. It depends on time of year, climatic conditions, season, and geographical location. So why we have to include KT? Because actually atmospheric effect is there in the insolation calculation or insolation determination or insolation prediction. That's why to consider the effect, atmospheric effect, we have to take into account KT values. So for modeling of KT, the data on the insolation on a horizontal surface over a period of time covering different season and climatic conditions for a few locations are to be measured. Means before modeling, we have to take data of KT for few locations and different climatic conditions or different seasons. We have to take the data because we know that for every modeling we require data. So you have to collect data for that. Based on the calculated value of extraterrestrial horizontal insolation or H0, what we have discussed earlier, and the measured global insolation or a horizontal surface, what is measured global insolation and what is calculated value, from that we can find out KT, we can compute for different locations. Then you have to plot KT versus the months, different months of a year. After that, Fourier series are considered as an appropriate curve fitting technique to model KT. How these are used and how to model KT, that we'll discuss. This is just how KT vary throughout the year. Starting from January to December, then again repetition, similar type. So this is the variation of KT throughout the year from the data. Now we have to model KT. So KT, let us represent KT by the following Fourier series. It is a function of say x wt plus some error. What is x? X is the latitude in degree phi minus 35. This 35 is an offset value, that is for Indian continental, this 35 taken, and for different other countries this value may change. And W is nothing but the total precipitable water vapor in gram per centimeter square, and T is 2 pi by 365 and minus 80, where N is the day number. So this kt is a function of xwt, and this fxwt is nothing but this constant a1 plus a2 sin t, a3 sin 2t, like this a7 cos 2t. So now these a's up to a1 up to a7, these a's are the functions of phi and w. How these are functions of phi and w, that we'll discuss. This a varies like this: small a I1, a I2, x, a I3, x square, w and w square, like this. So that means if you consider fxwt, first is a1. In the previous slide we have discussed capital A1. Capital A1 is nothing but if you put replace I equal to 1, that will give us capital A1. So we'll get this first expression. Then another is capital A1 plus A2 sin t. So if you replace I equal to 2, you will get like this. So now our objective is to update this small a coefficients so that we can find out the capital A coefficients, and after finding out capital A coefficient, we can find out this kt. And how to update this small a coefficient, that we can do using different artificial intelligence or signal processing or system identification techniques. So for that, this regression model is like this: fxwt equal to h into theta. Any, before applying any system identification technique or say subcomputing technique, system identification, or this signal processing technique or artificial intelligence, then you have to apply or you have to form the signal into a regressor form. Regressor form having two things: one is system structure, another is the unknown parameter to be updated. So here h is the system structure matrix and theta is the vector of unknown parameter, which we have to update using different techniques. So after multiplying this h and theta, you'll get this signal. So now if our updated unknown parameter will be more accurate, then our model will be more accurate. Model more accurate means we'll get more accurate value of kt. So if we'll get more accurate value of kt, then definitely we'll get the more accurate value of our solar insolation, which is kt multiplied with h0. So this theta we have updated using different algorithms such as recursively square, Kalman filter, and Ensemble Kalman filter. So I will not go in detail of this RLS and Kalman filter. Rather, that proposed technique is the Ensemble Kalman filter that I will discuss. So this Ensemble Kalman filter is just a modification or variation of the conventional Kalman filter. So in conventional Kalman filter, what we will do? There is updation of that covariance matrix of the state vector. But here, instead of this one, we used an ensemble matrix. We use a sample of state vector x, that is called ensemble. Based on that, this method is ensemble Kalman filter. So here, let theta updation we want, or theta updated using ensemble Kalman filter. So now for that, take this ensemble matrix as theta. Theta is what? Theta is nothing but small a coefficients which we want to update. If we will update these coefficients, then capital A coefficient will be updated. If capital A coefficient will be updated, then f will get good value or better value. Then accordingly our kt become more accurate. So this theta, for take the ensemble matrix as theta and the data matrix as f. So from this theta, we have to find out that expected value of theta 1 by q. Q is the total number of ensemble. So how many number of sample or ensemble we are taking? That is nothing but q. So 1 by q of this sum of these theta values, that will give us expected value. So after getting expected value, we'll get g, that is theta minus any value of theta minus its expected value. That will give us g. Then g transpose by q minus 1 will give us c. And this c matrix is used for updating this theta parameter or unknown parameter using this formula. So the how we are getting this one in detail, it is there in one of my publication, Ensemble Kalman filter based power system harmonics estimation, published in IEEE transaction of instrumentation measurement. Their detail of this thing is given. So basically here theta is updated using this equation. So we'll get updated value of theta. What is theta? Theta is nothing but our unknown parameter. It will be updated using this expression. So when theta is updated, then what we are getting? When theta is updated, then we will get small a coefficient a11, 12 up to a75, whatever we discussed in that large matrix, in the large equation. So after getting small a coefficient, we'll get capital A coefficient, because capital A in the expression of capital A, that small a coefficients are there. So if you know the small a coefficient after updating theta, then we can get this capital A coefficient. So after getting capital A coefficient, we'll get KT value, which is nothing but in terms of capital A coefficient, and this is the expression. So after getting this KT value and this H0 already calculated for a particular place for a particular time, then that H0 multiplied with KT will give us the global solar insolation on a horizontal surface at any location on any given day. So this is the scheme how this ensemble Kalman filter is used for accurate prediction or estimation or forecasting of global solar insolation. So whatever we have discussed, these are the steps. So quickly I'm discussing load data set of clearness index KT, means KT you have to find out, then you have to load it. Then input, what you have to input? Day of the year, latitude, and total precipitable water vapor, nothing but W. These you have to input. Then you have to calculate based on the equation or the model what you have discussed. You have to calculate delta, declination angle, hour angle omega SR, and extraterrestrial insolation H0. Then next step is to find out KT. For KT, initiate unknown parameter of theta. First you have to initiate theta value. Then model clearness index KT in the regressor form or parabolic parametric form, what we have discussed, F equal to S theta. Then evaluate estimation error. Error, how we have to estimate? That F minus that estimated value, that is H theta. Then calculate mean covariance of ensemble vector, that is expected value, and covariance matrix C you have to calculate. Then obtain estimate of ensemble vector, that is theta updation. If final iteration is not reached, go to step 6, evaluate error, then continue. Then finally estimate clearness index KT, that is theta. After finding out the theta, you can find out clearness index KT for a particular day of the year from final estimate of ensemble vector, which is nothing but theta. Then after knowing this KT value and H0 already calculated as up to step 3, then KT into H0 will give us global solar insolation forecasting. So here, these are the different locations from where measured insolation data are considered while developing the model. See, locations are named as say A to L, 12 locations throughout India taken, and see such a large variation of latitude starting from 8.48 degree latitude to 26.3 or to say 28.58 is such a large variation of latitude we have collected data. So data taken from different locations, say A to L, and data taken means January, February, March. Here the middle day taken, say n equal 15, the middle day of January, like middle day of February is 46. So like this data taken for different day, HM means the global solar insolation data, and W is the precipitable water vapor content data. These are the different data taken while developing our model. Then after this we have applied three methods we have applied. First is recursively square or RLS. What are the steps that I have not discussed here? So using different steps of RLS, we have forecasted or estimated the values of global solar insolation. See, for the different location, these are the 5 locations. Say these are the measured value, and HTC means these are the estimated value. So measured value and estimated value, there is some difference and error is there in the RLS estimation. Then next is the Kalman filter estimation. Similarly, different location, measured value and estimated value or forecasted value. And there are some error also. Then next is our proposed algorithm, that is measured and estimated insulation values using Ensemble Kalman filter. So these are the measured value of data for different months and for different locations. Am I audible properly?
Yes, sir, you're audible.
Sir.
Okay. So here also some error is there. How much is the error, or say how much our estimated value differ from actual value, that also will analyze using error analysis. Say these are the plots, that is these blue dots are the measured values, and these are the different using different methods, red dot and green dot and solid black. Solid black is the Ensemble Kalman filter using Ensemble Kalman filter estimation. So Ensemble Kalman filter estimation approaches more closely to that of measured value for city A in the northern part of India. For city B in the southern part of India, these are the figure and the curve. So similarly, we are seeing that there is more accuracy in estimation in Ensemble Kalman filtering as compared to other. Another is city C, which is in the eastern part. This is the result, that is estimation using Ensemble Kalman filter, more accuracy, more accurate as compared to other two. Then this is another city D in India, which is in the western part. So here this is the result. City E, that is central part of India. So here also the measured data and this estimation using Kalman filter approaching, but some still error are also there. Now, how much is the error, that error analysis? So every forecasting or this estimation technique is to be followed by error analysis so that we can verify how much is our error to our actual value. So the indices are, first one is the mean absolute percentage error, say MAPE. Then another indices is mean square error, MSE, and another is correlation coefficient R. Correlation coefficient R. These two should be minimized, but this R should be more. R should be more means how our estimated value or forecasted value approaches closely to the accurate value. So that depends on R. If R value is more, then more accuracy. So in this way, these are the three equations how these errors, these indices are defined. So MAP, mean absolute percentage error, mean square error, and this is the correlation coefficient. Now this is the comparison table for different city A, B, C, D, E, 5 cities we have taken, and different methods, RLS, recursively square, Kalman filter, and Ensemble Kalman filter. 3 methods we have taken for each city. MAPE error, we have found out that more error, little bit more error in RLS Kalman filter as compared to Ensemble Kalman filter. Mean square error is also less in Ensemble Kalman filter, and this R value will be more, means the estimated value is more closely to the accurate value. That's why R value close to 1 means if R value equal to 1, then fully 100% matches. If close to 1, then matches very closely. Then for city B, C, D, E, so for all these cases, the method when used, that is Ensemble Kalman filter, gives us very less value of means that MAPE and MSE error, and high value of R, that is this correlation coefficient. So same thing we have represented in the this diagram, that is C for city A, city B, city C, city D, and city E, and this symbol, this is the representation of Ensemble Kalman filter. C for all these cases, the MAPE error for different cities are less, and MSE error are also less for Ensemble Kalman filter. Then regarding the R coefficients are more for each case for Ensemble Kalman. That means that the actual value and the estimated value are closely matched. Now consider in the previous what we have discussed. So whatever the city, for example, we have taken data from 10 to 12 cities, and out of the 10 to 12 city, we have forecasted the value in any one city where also we have taken data. Now we'll use the same estimation algorithm for another city from where we have not taken data while developing our model. Means data not included in the model for the city X. So we have to check whether for that city also our algorithm works well or not. So here also similarly we have used three methods. So here also these are the measured value, that is 5.75 for example, and ensemble Kalman filtering, it is 5.6 coming. So like this is the plot. So here also it shows that even if data has not been taken from that city and we apply our model in that city for forecasting or estimation, it gives accurate or the closer result. Now this is the comparison of these indices, that is MAP, MSC, and that R value for city X. So we have seen that the MAP error, MSC error, all are less for using ensemble Kalman filtering for city X also, and this R coefficient is more. So from this, we concluded that forecasted value of insolation using this ensemble Kalman filtering, we get this more accuracy, and they are closely matching with the measured value or actual value. This method can be used for, even if it is developed in India, it can be used in any region in the world, because one of the testing we have verified taking city X whose data we have not included in the model. But for getting more accuracy in forecasting, our measured data should be taken over a large range of latitude. If you take a large range of latitude, then our model will be more accurate and our forecasting will be more accurate. Data should be more accurate as possible in order to calculate global solar insolation for a specific day, for a specific location. Nowadays, with the help of satellite, we'll able to get data for a region with good accuracy. So when our data is more accurate, then using proposed ensemble Kalman filtering, we'll get more accurate Fourier coefficient, or set these A coefficients. So if our A coefficients will be more accurate, then what will happen? Our KT value or KT estimation will be more accurate. If KT estimation is more accurate, then forecasting or the prediction or the estimation of solar insolation will be more accurate. Okay, I'm taking break for 2 minutes, then we'll discuss next part. Okay, so next is forecasting of solar irradiance using sky images. So whatever you have discussed till now, that was using the model based. Now it is using the image based. So here forecasting is primarily conducted on numerical weather prediction, that is NWP method, and satellite cloudy observation. But they provide the forecasting or this prediction several days ahead, which is not more accurate. Even if model based method also not more accurate as compared to this image based method. So for the short term solar irradiance forecasting, this image based method is more accurate. So for that, we have to capture the sky image. So for our analysis, the ground-based sky imager taken by instruments such as total sky imager. TSI is an instrument which captures the sky image. So we have to analyze from that image. Means, for example, we have taken image now and we have taken also image 1 minute ago or 2 minutes ago. So now you have to imagine or you have to analyze 2 minute ago image and current image. So how much is the cloud shifting in this between two images? If this much cloud shifting within this period, then if our forecast horizon is say half an hour, 30 minutes, half an hour, 40 minutes, whatever, after this, how much is the cloud movement? Then which portion of cloud will cover the sun? If thin cloud will cover the sun, then we'll get little bit more irradiance. If thick cloud will cover, then we'll get little bit less irradiance. If clear sky will cover, then we'll get more irradiance. So like this, we have to forecast from the image or cloud movement from the image analysis. That is the basically theme of this work. So TSI, total sky imager, able to capture sky image with high resolution, which provides us useful information for this forecasting of solar irradiance. For that, we have to use different image processing techniques and artificial intelligence techniques. So now, what are the different steps? So first step is pre-process sky image. For example, when we'll take or when the imager captures the sky image, then it is having a raw image. What is raw image? So from this raw image, what we have to do, how to pre-process it, that we'll discuss in the first step also, that is pre-process sky images. Then next step is determine the cloud pixel. From the image, you have to determine the cloud pixel. After determine the cloud pixel, then movement of the cloud. That is third step, forecast movement of the cloud. If the cloud movement is this much, then after this much time, what should be, the cloud should be at which position? Then that is called forecasting of movement of the cloud. Then finally, forecasting of solar irradiance. So each step we will discuss one by one. So this is just sky imager installed at School of EEE at NTU Singapore, where I did my postdoc work. So this is in the seventh floor building where sky imager is installed. So this sky imager is nothing but here a hemispherical mirror is there. So mirror capture this sky. So here and here is the imager enclosure where camera is there, and here image support arm, and each 30 seconds this sky imager captures the image and the data are stored. So taking this data, we have to analyze. So pre-process the sky image first step. Here this is the original sky imager, the sky image. So which contains different, if you enlarge it, you will see the images of building and site, different poles, different things are there. But our requirement is not all these things. So whatever our requirement, based on that, we will crop the image, crop the spherical circular image, remove the poles and building in the image by masking. So this is our cropped image. This is called pre-process the image, cropping of the image. We will take the required image. Then cloud determination. We know that each image pixel here we have classified into three categories, that is thin cloud, thick cloud, and clear sky. Three parts we have divided. Sky image having, it must contain three parts, either thin cloud, thick cloud, or clear sky. And if it will contain some other means that image of a beam or something, what you have seen that the camera is installed, one beam is there which connect that hemispherical mirror to the camera, that beam image also come. So that is not our requirement. That's why these things we have to omit it. So our image consists of three things. One is we have taken thin cloud, thick cloud, and clear sky. Then red channel and blue channel of each image pixel has been extracted and their respective R by B ratio, red to blue ratio calculated. Why this calculation is required? This calculation is required to classify this image or this part of this pixel falls on which category of image, whether it falls on thin cloud, thick cloud, or clear sky. That's why R to B ratio calculation is required. Then R to B ratio has been compared with a threshold value. Everything we have to compare with a reference value or threshold value. Then only we can classify if it falls beyond this boundary or within this boundary, this part, like this. Here also, this R by B ratio has been compared with a threshold value. In order to classify, it falls into which category. Then now question, how to get that threshold value? Which is our threshold value or reference, that how to get? So that is nothing but our clear sky library. Threshold value has been computed on creating a clear sky library. How to create a clear sky library? For that, we have to take a clear sky image that can be taken as reference. Where no cloud is there on a day, where sky is clear. So that image, that captured image taken as a reference. So from that image, we'll find out clear sky library. So in order to increase the accuracy of cloud determination, clear sky library has been compiled. So for that, for creating clear sky library, a completely clear day within the data. On the data set, we'll find out which is the completely clear day picture where no cloud is there. That we can take as a reference. So for that image, we have to find out R by B ratio of every pixel of that clear sky image and stored in a variable called RBR. CSL means clear sky library, that taken as a reference. This reference RBR has been used for comparison to classify the cloud. When you take any pixel, that pixel R by B ratio is to be compared with the R by B ratio of clear sky. Then difference you have to find out. That is called del RBR, difference of RBR of any pixel with this RBR CSL or RBR clear sky library. This is a clear sky image. And this is the clear sky library R by B ratio we have found out. This taken as reference. So to determine the threshold value, to classify whether a pixel falls into which category, thin cloud, thick cloud, or clear sky. So two different sets of training data are collected and compared with the R by B ratio of CSL. For each training image of thin cloud and thick cloud, so before verification, we have to take some training image. So in the each training image of thin cloud and thick cloud, we have to find out for each pixel, the region of pixel containing clouds had been recorded and its R by B ratio we have to find out. These R by B ratio we have to compare with the clear sky library we have already formed from the clear sky image. That gives us the delta RBR, change in red to blue ratio. That delta RBR we have to form in a histogram. Histogram of thin cloud RBR ratio and thick cloud RBR ratio we have to form. From the histogram, we have to find out what is the threshold value. How to find out that also we'll see. Based on the histogram, the mean value computed and treated as that mean value, whatever we will compute from the histogram, that we can treat as threshold value. So next slide. This is the training image. And here the thin cloud representation, R by B pixel of each thin cloud we have to find out. Then this is another training image. Then R by B ratio of thick cloud you have to find out. So whatever you have discussed, this thing represented in flowchart. Flowchart for cloud determination algorithm. So here, select a clear sky image and find out RBR CSL that already we discussed. One clear sky image you have to take and we have to find out red to blue ratio of this clear sky library. Then compute or CSL, that is clear sky library you have to form. Then input to closed date sky image for training the program. So closed date sky image you have to take and we have to find out what are the thin cloud and thick cloud pixel. Then after finding out thin cloud, thick cloud pixel, that can be, we can call it as RBR thin and RBR thick. Red to blue ratio of thin cloud, red to blue ratio of thick cloud. Then each red to blue ratio of thin cloud is to be compared with the RBR CSL to find out that difference. Del, that is called del RBR. Change in red to blue ratio, that change is with respect to clear sky line range. After finding out del RBR for both thin cloud and thick cloud, you have to plot the histogram. From the histogram, we will find out what is the mean value, and that mean value for thin cloud and thick cloud. So that will give us the threshold value for thin cloud and thick cloud, that we call as KT thin and KT thick. This is the histogram. So this is the histogram of thin cloud R by B ratio difference, that is del RBR, and what are the frequency in the y-axis. So from this diagram, we can imagine or you can see that the del RBR falls mostly in the region 0.1 to 0.2. And if you take mean value, then mean of all training data become 0.1575. So we can call or we can say that threshold thin value is 0.1575. Similarly, del RBR thick versus frequency we have plotted, and we are able to see that between 0.15 to 0.3, most of them are there. So mean if you take, you'll get point in between these two values, that is 0.2115. So we can treat that KT thin equals to 0.1575 and KT thick equals to 0.2115. In this way, you can find out the threshold value. Now, after getting this threshold value, our next job is to classify whether a pixel is under which category. That is our aim, to find out all this threshold value. So now we have found out threshold value. Next, our aim is to classify a particular pixel falls into which category, that is clear sky, thin cloud, or thick cloud. So this is given in this flowchart. Extract R by B ratio of each pixel and calculate del RBR. So if that del RBR is greater than whatever threshold thick we have calculated, what is threshold thick we have calculated? We have calculated as 0.2115. If del RBR is greater than threshold thick, yes, then we can classify this cloud as thick cloud. If this del RBR lies between thin cloud threshold and thick cloud threshold, that means this checking will say no, then we'll check whether del RBR greater than threshold thin. Yes, that means it lies between thin and thick cloud threshold. Then we can call this pixel as thin cloud. Otherwise, this pixel as clear sky. So in this way, we separate each pixel belongs to which category. So after separating, in order to see, we have to give different colors. So in order to display the cloud pixel classification results, so different color we have given. Say clear sky, we have given blue color, thin cloud given red color, thick cloud given purple, and pixels excluded means, for example, any bar, anything means that connecting bar between this camera to this mirror, that bar, its photo, its picture will also come, but that is not our requirement. So those pixels excluded in our analysis, so that we can give as green color. So after classifying the cloud pixel and giving color, what should be or how the sky image will look like. See, this is the original image where this is the raw image, building side, in the side buildings are there, photo buildings, everything there. Then we have cropped it. Then we have analyzed it. Each cloud pixel belongs to which category. We have given different color, and the pixel which are not required. These are the pixel not required. These are the photo of beam or something like that. So these are excluded from our analysis. That's why green, and clear sky given blue, thick cloud given purple, thin cloud given red. So this is our cloud decision image will look like this. Now, so up to second step over. So that means pre-process the sky image over, determination of cloud over, cloud pixel determination. Next is the cloud movement determination. So for that, we have to take two consecutive sky images. Say for example, 1 minute interval. You may take other value also. Two consecutive sky images with 1 minute interval will be fed into the optical flow algorithm to estimate the cloud movement. So optical flow algorithm will tell us what on seeing these both two images and analyzing it. So these two images will be compared and the cloud movement will be estimated. Say this is one image, 1 minute before image. This is the current image. There is some changes in the cloud movement. So optical flow will tell us how much is the cloud movement. Then now to display the cloud movement, total pixel in each image is divided into small boxes of 6 by 6 pixel for analysis. For example, each pixel are very small. So 288 by 288 pixel will divide 6 by 6 treat as 1. So now this 288 by 288 become 48 by 48 small boxes. Now optical flow algorithm display cloud movement by drawing red arrows in the direction from one of the boxes in the previous image to the corresponding boxes in the current image. Means what is the or in which direction cloud will move, that will be given by in the red arrow in the cloud movement. It can be shown the what is the movement of cloud, it can be shown by red arrows, and the length of the arrows will give us how much is the velocity. If length of the arrow is more, velocity is more. Length of the arrow is short, then velocity is short, like that. So magnitude of red arrows means the velocity of the movement. So now question, in a cloud, say we'll see 1 minute ago image, 1 minute or the current image. So in the sky image, so many clouds are there, and each cloud movement may be different angle or different direction. Then finally on which angle or which direction and what is the magnitude, how to find out? That we can find out using representative velocity vector. This is just an average speed, average, so many directions are there, so many velocity and values of velocity are there, or so many speeds are there for each cloud. Then we have to take its average and average velocity and average direction. That is called representative velocity vector. So determine the average speed and direction of the cloud movement to estimate the cloud location of next time step. So a representative velocity vector represent overall cloud movement. Means each cloud in a cloud, so many cloud pixels are there. Their movement may be different direction. Their magnitude of movement is also different. So in an average, what is the average velocity and what is the average direction? That finding out that one is called representative velocity vector. So here the small velocity vector with average speed less than 1 pixel, we have removed it because if you consider, then more noise may come or more erroneous result may come, so that these movements can be treated as noise and these are removed in the analysis. If Vi and Ui are less than 1, Vi means velocity in y direction, Ui means velocity in x direction. So if both are less than 1, then it means average speed is less than 1 and it can be recognized as noise. So in the analysis, these are removed. So after removing these noise vectors or after removing the pixels whose velocity are 1, the rest of the vectors are averaged out to get the mean speed and direction. That is called representative velocity vector. That is V equals to Ui square, that is x component square plus y component square, and theta is tan inverse b by a, just like our formula. So in this way, you can find out what is the one velocity or average velocity and average direction of the movement of a cloud. So whatever I discussed, these things are represented in flowchart. Get the cloud movement of every vector from optical flow algorithm. If checking of all the vector completed, then calculate the average speed and direction and draw the representative velocity vector. If checking not completed, then again you have to check whether ui less than 1, vi less than 1, both less than 1. Then if yes, then remove this vector, otherwise again analysis. So here you see that red, small arrow red marks are there. If you enlarge this figure, small arrow red marks are there, means movement of or the direction in which each cloud pixel will move, that direction given by small arrow. This small arrow may be in different direction, but after this representative velocity vector, we will find out here. Here you see a red mark is there with small red arrow. This is the representative velocity vector direction of this cloud. Single representative velocity vector from optical flow results. So after finding out this movement of cloud, means this arrow mark means in this direction, finally the cloud will move. Our next job is to forecast solar irradiance. So for forecasting solar irradiance, a clear sky global horizontal insolation GHI, clear sky GHI means global horizontal insolation. GHI clear sky library value had to be calculated according to geographical location, time and date of the year. So just like we've discussed in model also, GHI CSL is to be multiplied with KT value. So this GHI CSL value then multiplied by clearness index KT value based on cloud condition. Means whether we have to take this KT value for thin cloud or thick cloud or clear sky. So based on that, our final estimate will depend. So value of KT will be determined based on whether the pixel that cover the sun is consisted of thin cloud, thick cloud, or clear sky. So finally, insolation we have to find out global horizontal insolation CSL multiplied with KT value. But that KT, which KT we have to multiply, whether thin cloud or thick cloud or clear sky, that we have to find out. So after computing the KT values for all the three categories, three category means these three, thin, thick and cloud, clear sky. The solar irradiance can be forecasted based on the movement of the cloud by determining how the condition will be at the center of the sun at the time of prediction. Means at the time of prediction, whether center of the sun is covered by thin cloud. If it is covered by thin cloud, then you have to multiply KT thin value. If at the time of prediction, center of the sun is covered by thick cloud, then you have to multiply KT thick. Similarly for clear sky. Now this model for determination of GHI CSL means global horizontal insolation clear sky library. So for this is the model. This is called Inestian Perez clear sky model. In this model, the unknowns are A1, A2, FH1, FH2. So these depend on altitude. Using this expression, you can find out A1, A2, and some other unknowns theta z, AM. We'll find out how to find out in the next slide. Theta z is the solar zenith angle. What is solar zenith angle? So it is the angle between the vertical and the line to sun. So from the sun, if you take a line to any place, and that line with respect to vertical, what is the angle? That is solar zenith angle. From the sun, draw a line to any place, and that line with respect to vertical, how much angle caught? That is called solar zenith angle. Then I0 extraterrestrial normal incident irradiance that we have already discussed during model discussion. AM is nothing but optical air mass. AM is used in the previous, this expression AM is there. So this AM is nothing but optical air mass. What is that one? It is just a measure of length of the path through the atmosphere to sea level traversed by the light rays from the sun. From the sun to the atmosphere, to the sea level, how much the distance travel? It is just a measure of the length. That is AM, optical air mass. This AM can be found out using this expression, which requires theta z also, solar zenith angle. Then TL is nothing but link turbidity coefficient. Link turbidity coefficient is just a parameter which controls the attenuation of solar radiation reaching the sun under cloudless sky condition. When cloudless sky condition is there, what are the parameters which affects the attenuation of solar radiation before reaching sun? That we can take into account using this TL coefficient, that is called link turbidity coefficient. And I0 you can use this expression. So using all this, n is the day number. Using all this expression, we can find out this GHI CSL, Global Horizontal Insolation Clear Sky Library. So after finding out this one, multiplied with KT of a particular cloud, then you can find out our solar insolation. Now question, how to find out what is the KT value for different clouds? For example, for thin cloud, what is KT value you have to take? For thick cloud, how much? And for clear sky, how much you have to take? So that is called flow chart for computing KT value. So for that, compare current current sky image and its 1 minute ago image to obtain the representative velocity vector that we have discussed previously, to find out which direction the cloud actually moves. That is called representative velocity vector. Then after finding out this one, you have to extrapolate the velocity vector for 5 minutes. What is its meaning? For example, now it is say 10:56 a.m. For example, now 10:56 a.m. morning. So we have to pinpoint 3 minute ago image. 3 minute ago means if it is 10:56, 3 minute ago is 10:53 a.m. image. In a 10:53 a.m. image, we have to extrapolate for 5 minutes. 10:53 plus 5 means 10:58. So that means if we are now at 10:56 a.m., we'll predict 2 minutes ahead, 10:58 a.m. what is the cloud pixel. So that means that where the cross mark will fall. Determine the cloud condition of the cross mark. So if cross mark fall on a thick cloud, we have already discussed what is our figure or the image after all this coloring everything. Then that cross mark falls where? If it is falls in say red color, so that means this cross mark fall on thick cloud. So that means we have to find out what is KT thick. KT thick is how much? Irradiance, we can know the irradiance on that day at that time. What is the irradiance divided by GSI CSL? We have already calculated. Then irradiance by GHI CSL will find out KT thick. That KT value is KT thick. If that cross mark will fall on thin cloud, then KT thin will find out whatever irradiance divided by GHI CSL. In this way, we will find out KT thick, thin, and clear sky. This is the step to find out this KT value, just like training image or developing a model. So this is the step to find out the KT value. So after knowing KT value, we can find out what is our irradiance, solar irradiance. Determination of cloud condition. Here the extrapolation of velocity vector and 3 minutes ago cloud image. See, here the cross mark falls on say in clear sky. So that means we can say that here KT clear equals to whatever irradiance at that time divided by GHI CSL value we have already calculated, we'll get a KT clear value. In this way, we'll find out so many KT clear, KT thick, and KT thin values. And take this histogram to find out average value, just like we have calculated threshold value for different clouds. Similarly, we have to calculate KT value for different clouds. So so clear sky KT, thick cloud KT, thin cloud KT, different frequency. From this, we'll find out average value of KT. Clear sky is 818.243, and thin cloud is 395.958, and thin cloud is 569.55. Now we come to the point where we have already calculated what are the KT value for different clouds. So final step is the solar irradiance estimation. For example, whatever horizon you will take. You may implement forecast horizon of 10 minutes, 15 minutes, half an hour, whatever. Now, this is our final estimation. At this step, we already know what is the KT value for thin cloud, thick cloud, and clear sky. We already calculated. So now using this value, we'll find out what is our irradiance. So here also compare current sky image and 1 minute ago image to obtain representative velocity vector. Then similarly, just like we have used for KT computation, now we'll use same thing for irradiance calculation. That is extrapolate velocity vector for 5 minutes, pinpoint on 3 minute ago cloud pixel, and find out the position of X mark. Determine the cloud condition of the X mark, where the X mark falls. If X mark falls on the thick cloud, yes, X mark falls on thick cloud. That means irradiance equals to KT thick, which already we have calculated, into GHI CSL for a particular location, particular day, also we have calculated. So this multiplication will give us irradiance. Similarly, if X mark will fall on thin cloud, then we say that irradiance is whatever KT thin calculated multiplied with GHI CSL. In this way, we'll find out this X mark falls where, accordingly our irradiance will vary. So in this way, we will estimate our solar irradiance. So for example, here X mark will be pinpointed in 10:53 AM image. Based on the cloud condition result of 10:53 AM image, it can be seen that X mark falls in clear sky pixel. X mark falls C. X mark falls in blue. So blue means clear sky. So it is predicted that by 10:58 AM means what? Means now 10:56 AM. So 3 minutes ago is 10:53. 3 minutes ago image we have extrapolated for 5 minutes. So 10:53 plus 5 is 10:58. So that means we can predict that if now 10:56 AM, by 10:58 AM, clear sky will move to the position of the sun because X mark falls in the clear sky. That means you can predict it after this much time, this clear sky will move to the position of the sun. If clear sky will move to the position of the sun, then obviously we'll get more irradiance rather than any cloud comes to the position of the sun. So that's why, what is the irradiance? Irradiance prediction equal to GHI clear sky, whatever we have calculated, multiplied with KT clear. Why we are multiplying KT clear? Because X mark falls on the clear sky. So now KT clear, how much you calculated? 818.243. So multiplied with GHI CSL particular location, particular day, and whatever calculated. These two multiplication will give us the predicted value of solar irradiance. Now, this what we have calculated, it is how much accurate. We have to make error analysis, what we have done. So for example, what is the predicted error? Irradiance predicted minus irradiance actual or real divided by irradiance real. So actual irradiance from pyranometer data we obtained 744 and our analysis shows 757. So what is the error? Error is 1.574% only, so which can be granted. So now in this way you can able to forecast up to this much accuracy. That means error is close to means 1% more than just within 1 to 2%. So this is the solar irradiance forecast result for 1 hour on 30th July. So see 10 1 means within 1 minute interval images are taken. So 10 to 10:20. So cloud condition is very clear sky, thick cloud, thin cloud like this. And predicted irradiance is this value and real irradiance is this value. So error we have found out using the formula we have discussed. These are the different error we obtained. Similarly, then 22 to 40, 10:20 to 10:40. These are the results on the same day. 10:41 to 11 for 1 hour means totally 3 slides will show 1 hour, has shown 1 hour. For 1 hour, these are the different cloud condition, predicted irradiance, real irradiance, and prediction error. And we have found out average prediction error is 10%, which is which may not be acceptable. So some improvements required. So using this analysis, we come to know that we are able to predict, means our prediction matches to some extent the real value, but error is 10% coming. So we have to go for some modification. Where we have to do modification? So whatever you have discussed this thing in the here, see, that is a solid line is the real irradiance, and dash or dotted line, dash line is the predicted irradiance. So that prediction is not that much accurate. So you have to go for some modification. So what we have modified then? Where is our lacuna? So where is our problem actually in this estimation or forecasting? Our problem lies. What is our forecasted value expression? Expression is GHI clear sky into KT value. So if you're able to predict KT value properly, if our prediction of KT or estimation of KT or forecasting of KT is more accurate, then we'll get more accuracy in the forecasting of solar irradiance. So that KT updation we can do using different algorithms. Here AI, ML or any signal processing subcomputing technique will come into picture. That is, we have to update KT value. First, we have updated KT value using recursive least square algorithm. So RLS updated KT value and without RLS updated KT value, these are the two comparisons. So this side is sky image analysis, whatever you have discussed, plus we have updated KT value using RLS. And this side is whatever sky image analysis we have discussed, that only, no updation of KT value. So see here prediction error is little bit less in the RLS updated KT value. This is from 11 to 1120, then 1121 to 40, then next 1141 to 12 for 1 hour. So we have shown different results for on updating KT value using recursive least square and without updating KT value, means whatever sky image analysis we have discussed. Now, if you plot, so this predicted irradiance little bit approaches to real irradiance as compared to previous case, but also more accuracy we want. So that's why finally we have to go for updating clearness index KT value using variable Leaky least mean square algorithm. Now question, why suddenly variable Leaky least mean square algorithm? First of all, I have tested in so many algorithms and this variable Leaky least mean square algorithm before applying here, I have already applied in the power system area in the harmonics estimation, power system harmonics estimation. There we obtained very good result as compared to only least mean square or this Leaky least mean square or the variable step size least mean square. So I have compared in that problem and it shows that variable Leaky LMS gives better result. So then I have tempted to apply this variable Leaky LMS algorithm to this area. So that's why I have applied and it also gives better result as compared to recursively square methods. So here the same thing, regressor form of the model will come, that is signal or equals f equals to h into x. H is the GHI CSL, which is nothing but our system structure matrix, whatever we have discussed previously, and x, or we can say theta also. So that is the KT value which we want to update. So our unknown here is the KT value. So that KT value is nothing but the x vector or say theta vector also. That KT value you have to update using this variable Leaky least mean square algorithm. So this is the equation or the model of this variable Leaky least mean square algorithm. How it works, all this thing I am not explaining. So this is there in this publication. This is one of my publication published in IET, Science Measurement Technology. So in this publication, how this expression derived, everything, all the backgrounds are there. So if you want, you can verify also, you can see also. So this is the updated equation to update that x value. X value is nothing but KT here. KT means we want to update KT value for three cases. Three cases means clear sky, thin cloud, thick cloud. All these three cases we have to update KT value. That means X is a vector having 3, 1 plus 3. So now this is the updation. So here it involves what? Error equals to what? Error equals to the signal minus its estimated, or F minus H theta. H theta is the estimated. Actual minus estimated is the error. This error we have to minimize. So for this error minimizing, this is the final step. And before that, what are the steps? Before that, these are the steps. These are the steps means step size. Mu is the step size you have to update using this relation. R is the autocorrelation matrix. We have to update using this relation. So we have to update mu, step size, R. Then leakage factor we have to update like this. Gamma is the leakage factor. After updating mu, R and gamma, finally X is updated in this equation. So in this X updated equation, R, gamma, mu, all are updated. That is, mu is updated, gamma is updated, and finally this X is updated. Another explanation I am going to tell here in this, why this VLLM's algorithm is in particular better as compared to only LMS, because here the cost, while taking the cost function in the VLLMS algorithm, we have used one regularization parameter. That cost function is added. That one is added in the cost function. Because of that, what happened? Because of that, it will not allow the drifting of parameter from its usual value or actual value. That means parameter drifting is avoided. So these all things are discussed in this paper. And regarding the other parameters during this application of this algorithm, we have used so many parameters like this. And finally, we obtain KT clear sky as 826, updated value using VLLMS, that is variable leaky least mean square, KT thick cloud 435, KT thin 591. So these are the final updated KT values using this variable leaky least mean square algorithm. See, this is the result showing in the here. This is only sky image analysis. Whatever you discussed, KT is not updated. This is sky image analysis as well as KT is updated using VLLMS. That is VLLMS updated KT. And for each case, see, images are taken from 11 to 1120 like this, 21 to 40 and 42 that 12 for 1 hour. So cloud condition, predicted irradiance, prediction error. Here also cloud condition, whether this algorithm is able to find out cloud condition same or different, predicted irradiance, how much differ from the actual irradiance, and this actual or real irradiance is this side given. So what is the prediction error? For each estimation as compared to real irradiance, how much error also we have calculated. This is 1121 to 1140 image, then 1141 to 12 o'clock. That is, it covers 1 hour image. So now this is the overall result, whatever I have shown. See, in this result, this real irradiance is the solid line and this dashed line is the predicted irradiance. See, using VLLMS updated KT value, our predicted irradiance and real irradiance closely matches. So this matching is more perfect means as compared to previous cases. So how much perfect or how much accuracy in order to find out, we have to go for this indices. What are the indices? One is the mean absolute percentage error, that is MAPE error. So MAPE error is 7.562 for predicted without any KT updation, that is only sky image analysis. And if KT is updated using recursively square, this error is coming 6.565. And here VLLMS is using VLLMS 3.537% MAP. So now, so we have discussed for successful application of short-term solar irradiance forecasting using sky image. That means how, starting from capturing of sky image to how to forecast, that is pre-process sky image, then all these cloud determination, cloud movement, then forecasting. So how these steps can be done, that we have discussed, and we have found out that this algorithm using this KT updated VLLMS updated KT value able to predict more accuracy in solar irradiance as compared to other methods. So this forecast horizon can be changed as per need. For example, we need forecast horizon of 1 hour or 30 minutes or 40 minutes like this, so it can be changed. And this forecast, whatever we have discussed based on sky image, in our discussion we have discussed the images captured by TSI, total sky imager. So except this one, other type of imager are also there. So if you capture image from other type of this image enclosure, imager, then also we can apply this algorithm. One of them is say versus image, just like TSI, one is versus image. So if you capture image from that also, then we can analyze using this algorithm, no problem. Then by switching on or off the backup storage beforehand, means if you're able to forecast or predict solar irradiance beforehand, then we can manage, just like I've discussed, we can manage our scheduling. So the solar intermittency issue, which is the main problem, uncertainty or intermittency issue, can be solved and damage to the system can be avoided. These are the different references. Thank you. Any query? Arnav sir, are you there?